In the previous class, we followed one build from configuration and layers to a finished image. This time we open the decisions bitbake made along the way. We will ask 5 questions of a completed Yocto 6.0.2 Wrynose build. What is the effective value of a variable, and where did that value come from? When several recipes could satisfy a dependency, which one is chosen? What does the task dependency graph of the image actually contain? Why can most tasks be restored instead of rebuilt? And where does a single task record what it did? BusyBox will again be our traceable component. By the end, you will be able to read bitbake's choices from its own tooling instead of guessing them. Bitbake keeps every configuration and recipe value in a single data store. A variable's final value is not written once. It is computed from many operations spread across configuration files, distribution policy, machine settings, classes, and the recipe itself. An assignment can set a default, append to it, prepend to it, or override it for a condition. Because of that, reading one file tells you what that file intended, not what bitbake resolved. The documentation gives us 2 ways to see the resolved result: the full environment dump and a focused query tool that also reports the value's history. We will use the focus tool. Every query in this class runs against one prepared workspace. It uses the stock Pokey reference distribution, the 64-bit x86 QEMU machine, and the minimal core image from Wrynose 6.0.2. That build was completed before filming, so its metadata cache, shared state cache, task stamps, and task logs already exist. We open the pinned build environment once and run the queries there. These commands parse metadata and read preserved files. They do not compile a recipe, rebuild the image, or boot it. That boundary is what lets us read bitbake's decisions without changing them. Our first query asks the datastore for one distribution policy variable and for the record of how it was built. This variable controls broad feature policy for the whole build, and it is a good example precisely because no single file sets it alone. The query tool prints 2 things: the history, which lists each operation that touched the variable and the file that performed it, and the final computed value at the bottom. Watching both together shows the difference between an intention in one file and the result bitbake actually uses. Here is the query. The output makes the earlier point concrete. The history block names each operation and its source, so we can see the value assembled step by step rather than appearing from nowhere. The final line is the value bitbake will use for this target. This is why the environment query is the authority. It collapses configuration files, distribution policy, and any conditional overrides into one resolved answer, and it shows the provenance behind that answer. This check proves how one variable resolved for this build. It does not prove that any recipe compiles, it only reports a computed value. Some dependencies do not name one recipe. A build may need a kernel, an init system, or a C library, and more than one recipe can offer to supply it. Bitbake handles this with providers. A recipe declares what abstract capabilities it provides, often through a name that starts with the word virtual. When several recipes provide the same capability, a preference variable selects which one is used, and a second preference variable can pin which version is used when a recipe exists in several versions. This is how a build stays deterministic even though the metadata offers choices. We can read the chosen provider directly. We ask which concrete recipe supplies the kernel capability for this target. The first query returns the preferred provider for the virtual kernel name, the reference kernel recipe selected by this configuration. The second query lists that recipe across the enabled layers with its version. Together they show the resolution in full, an abstract capability on one side, and the specific recipe and version chosen on the other. Read the exact value shown on screen rather than assuming it. This selection is made when metadata is parsed. It identifies the recipe that would be built for the kernel. It does not by itself prove the kernel was compiled. Provider selection answers a question that a plain dependency list cannot. The abstract name says what is needed. The preference variables say which recipe and which version satisfy it here. A different machine or distribution policy could select a different provider from the same metadata, which is why two builds can share recipes yet resolve dependencies differently. Having settled which recipes participate, the next question is how those recipes connect to one another and to the image as ordered work. That relationship is the task graph. BitBake does not run recipes as isolated units. It expands them into tasks and connects those tasks with dependencies. A build time dependency says one recipe's output must exist before another recipe's task can run. A runtime dependency says an installed package needs another package present on the device. The documented way to see this structure without building is to ask BitBake to emit its dependency graph. The graph is expressed at the level of tasks, not just recipes, because the real ordering constraints live between tasks. We will generate that graph for the image and then find BusyBox inside it. This command asks BitBake to parse the image target and write its dependency graph to disk. It is a metadata operation. It resolves and records relationships, but it does not fetch, compile, or assemble anything, so it is safe to run against the completed workspace. Because this workspace was already parsed, this is a warm parse rather than a first one. When it finishes, it leaves two files we will read: a build list naming every recipe pulled in by the image, and a task dependency graph describing the edges between tasks. Here is the graph generation. The graph is large, so we read only the part that concerns our component. Filtering the task graph to BusyBox shows edges from its tasks toward the tasks that consume its output, ending at the image's root Silvasichin assembly. Each edge is one ordering rule that BitBake must respect. The build list confirms the other half of the picture. BusyBox appears as one recipe among the many the image requires. This is the structural view behind last class's observation that a single image target expands into a much larger graph. It shows ordering and membership. It does not tell us whether each task ran or was reused. That answer is in the signatures. BitBake avoids repeating work by hashing the inputs of each task. Every task gets an input signature computed from its code, its variables, and the signatures of the tasks it depends on. Before running a task, BitBake checks whether output for that exact signature already exists in the shared state cache. If it does, the task is restored from that cache instead of executed, and this restore path is called a setscene task. If any input changes, the signature changes, and the task runs again. This mechanism is why the warm build we are inspecting completed quickly, and its evidence is written into the build's stamp files. The stamps directory records which tasks completed for BusyBox, and each stamp file name carries the task's input signature as a long hexadecimal suffix. That suffix is the hash bitbake compared against the shared state cache. Many of these entries end in the word setscene, which marks a task that was restored from shared state rather than executed here. So the stamps are not just markers that a task finished. They show how it finished. When you need to know why two builds diverged, the documented tools dump one signature or compare two of them to reveal exactly which input changed. That is the debugging path built on the same hashes. It is worth stating the limit of this mechanism clearly. A matching signature means BitBake believes every recorded input is unchanged, so it trusts the cached output and restores it. It does not reread or re-verify the restored binary. The guarantee is about inputs, not a fresh inspection of the result. A changed variable, patch, or dependency signature produces a new hash and a freshly executed task. This is exactly why reproducibility depends on controlling those inputs, a topic a later class treats on its own. For now, the stamps have told us which tasks ran and which were reused. To see what a task actually did, we read its log. Bitbake writes a separate log for every task it runs. Inside a recipe's temporary work area, there is a directory that holds one log file per task and one generated script per task. The log captures what the task did and any messages it produced. The generated script is the exact code Bitbake executed for that task, and a task order record shows the sequence in which the tasks ran. This per-task granularity is what makes a failed build tractable. Instead of one enormous stream, you open the log for the single task that failed. We will open one BusyBox task log to see the shape of that evidence. This is the log for a single BusyBox task. The file name names the task, and the body records the actions and messages from that task alone. Because much of this build was restored from shared state, some of these logs belong to setscene tasks, which is consistent with the stamps we just read. The point is not any one line. It is that Bitbake's output is not a single undifferentiated stream. It is a structured set of per-task records, each tied to a recipe, a task, and the signature that decided whether the task ran. That structure is what turns a wall of build output into something you can navigate. We can now read a build as a sequence of decisions rather than a mystery. A variable's value came from many operations, and the query tool showed both the result and its history. An abstract dependency was resolved to one recipe and version by preference variables. The task graph showed how BusyBox's tasks connect to the image's assembly. Each task carried an input signature, and the stamps showed which tasks were restored from shared state instead of executed. Finally, each task left its own log. Every one of those conclusions came from an artifact Bitbake produced, and none of them required rebuilding the image. We read Bitbake's decisions on a stock build, variables and their history, providers, the task graph, signatures and stamps, and task logs. Next, we stop only reading the stock build and begin extending it, adding a layer and a recipe of our own, and watching these same variables, providers, and signatures respond to the change. Subscribe to continue.